How you doing? I'm Mr. Rose, and finally, we're starting capacitance all the way up in the front of the room. So, first of all, what is capacitance? Capacitance is really just a way to store charge. We've stored things before. What have we stored before? We've stored potential energy before. How do I do that? Well, if I really want to store some potential energy, I dig a hole. I fill that hole with water like I did there, and now I have this little man-made lake. Well, if I start pumping water up into the top of that chamber, I build this little chamber here, I have a little container up there, and I start filling water up into that container, I am storing some potential energy. Now, if I want to increase its potential, I'm just going to make my container higher. How do I increase its potential energy? Well, to increase its potential energy, that's easy. I can make my bucket bigger. If I make the bucket bigger, I can get more water in there. So, I'm raising this water up a little at a time, little at a time, little at a time, and I'm filling this bucket up with water. So I fill that bucket up with water. How do I get that energy back now? I stored all of that energy. Well, if I add a little spigot here, and I let my water flow down, that energy, that water, falls down because of the force due to gravity. As that's falling down, that's giving me the energy back because we know this is a conservative force. We're going to do the same thing with charge. But to do it with charge is a little bit harder. I could say have two charges, a proton and an electron, and I can separate them out. As long as I'm holding them here, I know that they want to come together. Why do they want to come together? Because we know opposite things attract. This ends up being a problem because I can't walk around the rest of my life holding a proton and an electron. I'll get tired. I want to use my hands. So what we did is we invented this capacitor. So what I have here are two conductive surfaces of any material. I misspoke. I apologize. Two conductive surfaces of any orientation. It does not matter the geometry of these things, so to speak. I want to start pulling off charge. So what I'm going to do is I'm going to take a Q and I'm going to move it over there. Take a Q and move it over there. Take a Q and move it over there. And eventually, I have a bunch of negatives on that side, I have a bunch of positives on that side, and I've created a potential difference. I know that there's more positive things there. I know there are less positive things there, thus it's negative. And I know as I continue to move that, the moving takes work, and with every charge I move over, it's going to be more difficult. I'm increasing, so to speak, the potential on that side. As I do that, I create this potential difference, where I've called the orange B, potential difference V, the purple A, potential of V prime. Now I know that creates a potential difference between V prime and V. Well, I'm going to simply define my capacitance as how much charge I'm moving over, all of those delta Q's, based on that potential difference, divided by delta V. Well, just like we've spoken about now several times, I need an arbitrary starting point. It doesn't matter what those two values are. All that matters is the difference. So to make life easy, we set V prime equal to 0. If I set V prime equal to 0, now by definition, my capacitance C is equal to charge per unit volt. A coulomb charge per potential difference, charge per volt. A charge per volt is something that we've come to know as a farad. Now, a farad, when we get into them, are very, very big numbers. So we typically deal in real life with microfarads, something very small as opposed to these giant farad numbers. Let's give you an example. The simplest capacitor we use is a parallel plate capacitor. So I have this parallel plate capacitor, and what I'm going to do, I know that it's a single plate. I know the area of that plate is A. I'm going to separate those two things out by some distance D. Now, I'm going to start to move charges from the bottom plate to the top plate. As I do that, just like we did over here, I'm going to start having one plate positive, one plate negative, because I'm physically moving charge from one to the other. Well, as I physically move charge from one to the other, just like we happened over here, it's going to become more and more and more and more difficult. How am I actually physically moving charges? I'm not just moving a charge with my fingers. Obviously, we can't do that. So what we're going to do is, it's a little bit of a stretch, but it'll help you understand. We're going to recall our unit of an electron volt. What is an electron volt? An electron volt, by definition, is the amount of energy it takes to move one electron through a potential difference of 1 volt. So what I'm doing is I'm applying a voltage to that parallel plate. We've avoided the word voltage for a long time. This potential difference is just a voltage. So we know that if I apply a voltage to that, if I'm creating a potential difference, I get to move charges. And I know those moving charges are going to give me some electric field. And I have a very simple formula. Potential is equal to the electric field times the distance. Well, we proved in our last lecture, we reviewed, I should say, in our last lecture, that the electric field in between two parallel plates, we used Gauss's law for that, gets me sigma divided by epsilon naught, where sigma is my charge per unit area. Luckily, I know the area of my parallel plate. So if I know sigma is charge per unit area, and I know my potential difference now is my electric field, sigma over epsilon naught, times distance, a simple substitution gets me my potential in between those parallel plates, or my potential that I get from that. Q divided by A epsilon naught times D. Well, now we finally started talking about capacitance. What is the capacitance? The ability for it to store all of that charge. Capacitance is equal to Q divided by V. Well, I can rearrange for Q, and I could say that capacitance is the area of my parallel plate, or the area of my capacitor, times epsilon naught, my permittivity constant, divided by the distance those plates are separated. This is a huge statement. First of all, it gives me the capacitance, or the ability to store charge on a parallel plate. Second, notice it is related only to the area of my plate and how far apart they are. It is not related to all of these seemingly electrical things. I can figure out the capacitance really just on the orientation. Sounds familiar. I could figure out how much energy I could store based on the size of my bucket. It is a very good analogy back to things that we understand very well with this gravitational potential energy. So our general rules for finding capacitance I have set up over here. First thing we want to know is we want to either know or estimate our geometry. My picture I have over here, if I had some weird shaped capacitor, I might estimate that to be a rectangle, or estimate that to be a circle. Estimation gets us a very good number. Or hopefully I know the geometry, like a parallel plate, a flat plate, or a sphere, which is our next example. Once I do that, we're going to assume the charge on each are equal in magnitude, opposite in sign. Because if I move an electron from there to there, if I move a proton, say, from there to there, a positive test charge, excuse me, as I'm moving charges, obviously I have a conservation of charge. If I move 4 charges on the top, I lost 4 charges on the bottom. That has to be. We're then going to calculate the electric field between two parallel plates, which I did. Electric field between two parallel plates. I just happen to know it. If I don't, we're going to use Gauss's law, because that's very easy. From there, now that I know my electric field, I'm going to calculate my potential difference. Delta V is equal to negative E dot dr. And I'm going to integrate about the line I'm moving my charge from the bottom plate to the top plate. Lastly, my capacitance is equal to Q divided by V. It's just a simple plug and chug to find my capacitance. So now that we have these general rules, let's show one more example. I want to find the capacitance of the spherical capacitor. So what do I know? I know I have an inside sphere called radius A. I know I have an outside sphere, radius B. And a capacitor right now is filled with nothing. There's just empty space in here. So I have a conducting sphere with nothing in between. So my goals of this are to find my electric field. I'm going to integrate about the line that I move charge. I'm going to divide my potential difference that I found with my integration by Q to find my capacitance. So we first start by moving some charge. So I'll get some charges there. I'll get some charges there, which means I moved my charge from A to B. I'll put a little Q there. Move my charge from A to B. That's the line I'm going to integrate at. The hard part is starting, finding this electric field, and this is what people have a problem with. So we recall Gauss's law. For Gauss's law, I need a Gaussian surface. I need to enclose something. There is a Q and an epsilon naught, a charge enclosed. So I'm going to draw a Gaussian surface right around A. Now that I drew my Gaussian surface, I can find my electric field in that Gaussian surface. In other words, the charge by A is my charge enclosed. It's going to act almost like a test charge, or a point charge, I should say. So, moving this over, I know the electric field inside my Gaussian surface because this sphere is going to act like a charge, just spot right on the center, is equal to Q over 4 pi epsilon naught times 1 over r squared. I'm going to integrate to find my potential difference, negative E dot dr. I can pull out all of my constants, so I'm just integrating about my r squared. Well, r squared is my difference, my radius there and my radius b. So when I take my integral of 1 over r squared, I'm going to be left with 1 over r, which is 1 over a minus 1 over b. I rearrange to solve for q, which takes some algebra, and now I have my charge is related to my potential difference times my constant divided by the difference of my radius, 1 over a minus 1 over b. Last step, c is equal to q over v. Plug that in, c is equal to q over v. A little bit of algebra gets me the capacitance for a spherical capacitor, and that is 4 pi epsilon naught AB divided by B minus A. What if I wanted to check that? If I wanted to check that, I can make, again, some gross approximations. So what am I going to do? This is my favorite part of this lecture. What I'm going to do is I'm going to take that spherical capacitor that I had. And some people think, oh, let's shrink it down. No, we're not going to shrink it down. We're going to make it huge. It is going to be the biggest huge capacitor you've ever seen in your life. So I'm going to make it huge, but when I do that, I'm going to make the distance in between A and B very small. Essentially like when I look outside at planet Earth. I believe Earth is flat where I see it. I know Earth is not flat. Don't go viral with that. Earth is very spherical. But right out my window, Earth is flat. So we're using the same thing. If I make it huge and I only look at a very, very small area, a small part of it, I can say that A times B, well, A and B are pretty much the same thing because it's so big. So A times B is just going to be R squared. And B minus A, well, that's almost the same thing. That's just my distance away, D. Now, all of a sudden, instead of these two spheres, I'm looking at something that's kind of like a parallel plate. So I have my capacitance, 4 pi epsilon naught R squared divided by D, where 4 pi R squared was just my area of that sphere. So now I replace epsilon naught A over D. That is my capacitance for a parallel plate. That doesn't mean it's 100%, but it means it's a good approximation. That means it's probably in the right direction. Last thing I want to do, it's a long lecture, I'm sorry. How much energy does it take? Because we've been talking about energy. Well, how much energy does it take to charge my capacitor? Got my positive side, I got my negative side, and I'm going to move those charges up against my electric field, which means I'm doing work. I'm going to utilize that work energy there. I know a little q, d work, dw, is equal to dq times v. Well, v, my potential difference, knowing that my capacitance is q divided by v, I could say that v is q divided by c. So now it's in relation to my capacitor. I integrate both sides. The antiderivative of dw is just the work. The antiderivative of dq times q over c is 1/2 q squared over c. Then I have a work formula. I can also rearrange, instead of terms q, I can use my c is equal to q divided by v, and I can say work is also 1/2 capacitance times v squared. Thanks for watching again. That's all I have for you today on our introduction to capacitance. Please like, comment, subscribe, and I will see you next time. Remember, this was huge.